students, today we are going to see the recap of 50 unit. Very important and it talks about the future trends of data analytics and things like that. I just would like to recall back the thing which has been covered in the last few classes regarding the unit 5. So the predictive modeling involves using statistical or machine learning methods to forecast future outcomes based on the historical data. In chemical and process engineering, it is crucial tool for optimizing the operations, improving the product quality and enabling the real-time process control. The key objectives of predictive modeling in process industries: forecast process behavior under various conditions, enhance decision making using data driven insights, improve operational efficiency and reduce cost, support real time control strategies, example model predictive control, reduce downtime by anticipating the failures or quality issues. Coming to the components of the predictive modeling, the sources for data collection are sensors, distributed control system, supervisory control and data acquisition, and LAMS. So the types are time series, categorical, and continuous. So in the last class, we have discussed what is the LAMS, sources of data. So LAMS is nothing but is a laboratory information management system, integrates data from various sources to manage and track samples, workflow and results. So this includes direct data capture from laboratory instruments, sample metadata and results from analysis. LMS also manages data from external sources such as third-party labs or data warehouse. Okay, so laboratory information management system. So there is a source, okay, integrates the data from various sources to manage and track the samples, workflow and results. Data pre-processing, cleaning, normalization, scaling and feature engineering and selection. Components of predictive modeling, statistical methods, linear regression, ARIMA, machine learning models, decision tree, random forest, support vector machine, deep learning models, neural network, a long short-term memory, okay, for time series, and model training and validation, split data set, okay, performance matrix like root mean square error, mean absolute error, R square, and the cross validation for robustness. So what is process optimization? So we have discussed what is process optimization in the last class. Improving process parameters to achieve maximum yield or purity, minimum energy or resource consumption, reduce environmental impact. So how predictive modeling helps? Simulation of scenarios before implementation, optimization algorithm, example genetic algorithm can use predictive models to find the optimal settings, integration with the digital twins models for real-time feedback. So the traditional versus predictive control. So this is traditional control is reactive, whereas the predictive control is proactive, feedback based. This one is model based, less adaptive and highly adaptive. So process control using predictive modeling, model predictive control. Okay, so uses a dynamic model to predict the future planned output, solves an optimization problem at every time step, incorporate the constraint on input and output. So when I teach you this thing which I told you, model predictive control, okay, we could be able to implement the um, variation and try to adjust accordingly. For example, the spray dryer, I told you the additive will be added in order to avoid the stickiness, how much amount of additives need to be added, okay, in the spray dryer before it has been injected, sample has been injected to the spray dryer. Okay, so the broader predictive control will, we can put a sensor and then we try to manipulate the variable so that the any deviation occurs, okay, the stickiness is increased, obviously the input value can vary and then we can able to have the control and a real time scenario. Okay, so benefits of multiple what you call model predictive control and its multivariable systems will predict and avoid the consistent violation, constraint violation, adaptable to non-linear time varying process. Okay, so application of chemical engineering model predictive control, okay, especially the predictive predictive control, okay, distillation column control, predict product composition based on reflux ratio and feed condition, optimize energy consumption, bioreactor monitoring, predict biomass, product concentration, control temperature, pH, feed rate, catalytic reactor optimization, model reaction kinetics using historical data, optimize the temperature and residence time. Coming to the tools and performance, so you can use Python, okay, this scikit-learn, XGBoost or TensorFlow, MATLAB or Simulink, Aspen Plus or Aspen DMC. So we have elaborately explained what is Aspen DMC and things like that. Okay, PA system and data analytics too. So challenges and consideration: data quality, availability, model interpretability versus complexity, need for domain knowledge integration. Okay, so and the model drift over time requires retraining. So it's not actually without domain knowledge it's very difficult to analyze the data. Okay, so domain knowledge is very important in the integration part. Further future direction: integration with IoT, industrial IoT, in the industry Internet of Things and edge computing. Okay, self-learning models with reinforcement learning. Okay, more robust hybrid models combining physics-based and data-driven methods. The summary of predictive modeling is a cornerstone of modern process engineering, enabling smarter, more efficient operations. It is synergized with optimization and control techniques, leads to enhanced safety, profitability, and sustainability in process industries. Coming to the quality control in chemical manufacturing, definition of quality control, importance of quality control in chemical industries, good manufacturing practices, regulatory standards like ISO, FDA, Food Drug Administration, good manufacturing practices, critical quality attributes, okay, critical quality attributes, tools for quality control, SPC, control chart and Pareto analysis, 80-20 rule. Okay, so quality control is a set of procedure and practices aimed at ensuring that chemical products meet defined standards of quality. It involves monitoring manufacturing process, detecting deviation or defect, okay, implementing corrective action. So corrective action is very important, so that then only you could be able to achieve a maximum yield or maximum safety and things like that, reliability, okay, and so on and so forth. So the goal is to produce consistent, safe, compliant products while minimizing the waste and variability. Coming to the quality control is critical in chemical manufacturing due to health and safety, regulatory compliance, customer satisfaction, cost efficiency, and process optimization. Coming to the health and safety, chemical products often involve hazardous materials. Quality control ensures safety for end users and operators. Regulatory compliance: industries must comply with strict regulations like FDA and EPA. Customer satisfaction: high quality products enhance trust and loyalty. Cost efficiency: detecting defects yearly reduces rework, waste and recalls. Process optimization: quality control data helps improve production efficiency. To maintain the quality, manufacturers follow international standards. ISO 9001 focuses on quality management system. Good manufacturing practices set by FDA and WHO, World Health Organization, crucial in pharmaceuticals and food. ICH Q8, Q9 and Q10 are the guidelines for quality risk management in pharmaceutical industry. So we will see actually during while taking the class I didn't explain elaborately actually the ICH Q8, Q9 and Q10. I'll let you know what these mean. So it's a guidelines for quality risk management in the pharmaceutical industry. So ICH Q8, Q8. Okay. So then ICH Q8 is a, what is ICH Q8? ICH Q8 is a guideline from the International Council for Harmonization focused on pharmaceutical development, particularly emphasizing a quality by design approach. So while taking a class, I told you actually the people come from the industry doing the IACC talk. They are talking about the quality of the things. So unless otherwise the quality is not been recognized by the FDA, they won't approve the things, right? So ICH Q8 is a guideline from the International Council for Harmonization focused on pharmaceutical development, particularly emphasizing a quality of design approach. It provides a framework for developing and optimizing the drug formulation and manufacturing processes to ensure consistent product quality. So the key aspect of ICH QA8 include quality by design. This approach focuses on understanding and controlling the critical quality attributes throughout the development and manufacturing process to ensure consistent product quality. Design space ICH-Q8 encourages establishing a design space which defines the acceptable range of parameters for material attributes and process parameters within which the product consistently meets its quality target product profile. Risk assessment. The guideline emphasizes a risk-based approach to identify and manage potential issues during development and manufacturing. Continuous improvement. ICHQ8 promotes continuous improvement and learning throughout the product life cycle using knowledge gain to refine processes and optimize the product quality. Coming to the scientific justification, the guideline encourages the use of scientific understanding and experimentation to support the development and optimization of pharmaceutical products and processes. In essence, ICHQ8 provides a structured and scientific approach to pharmaceutical development, aiming to ensure consistent product quality and improve manufacturing efficiency. So, ICHQ8, Q9 and Q10 provide a structured way to define the product, critical quality, attributes, design space, the manufacturing process and the control strategy. So, the main aim of ICH, Q8, Q9 and Q10 provides a structured way to define the product quality, attributes, design space, manufacturing process and control strategy. So, it's a guideline for quality risk management in the pharmaceutical industry. REACH and OSHA. Chemical safety and environmental production regulations. Example, the pharmaceutical manufacturer must maintain consistent pH levels in a drug formulation. Deviation could make the product ineffective or harmful. Critical quantity attributes. So, these are the physical, chemical, biological or microbiological properties that must be controlled within the specified limit. So, the example of critical quality attributes, the pH level, viscosity, reaction temperature, purity or impurity profile, particle size distribution, CQAS are defined during product development and become key metrics for ongoing quality control. The several tools for quality control are used to monitor and maintain quality. Statistical process control uses statistical methods to monitor process behavior, helps detect anomalies and maintain control limit. Control chart track specific process parameters over time. Example, exact chart, mean and range, P chart, proportion defective, parent group analysis, 80-20 rule, identify the most common source of defects. Okay, helps prioritize efforts for quality improvement, histogram and scatter plot, root cause analysis, okay, fishbone diagram and 5Y techniques. So the 5Y techniques actually is a root cause analysis tool for the quality control. So let me explain. During the normal previous classes, I didn't explain very much in depth actually regarding the 5Y techniques in the process control, quality control. Okay, so let me explain about this particular which has been missed out, 5Y techniques in quality control. Okay. So, the 5Y techniques is a problem solving method used in quality control to identify the root cause of a problem by repeatedly asking why. So, why this has happened, why this has happened and why this has happened. By repeatedly asking the question why, that will help you to identify the root cause. Okay. So, by asking why 5 times or more if needed and focusing on the answers, you can dig deeper into the underlying issues and find the true root cause. So anything is not be a quality control, even for any process, why this is occurred, why this is occurred, why this is occurred. If you keep on asking the question why, that will help you to find the baseline information as well. Okay, so identify the problem, how it works, identify the problem. Clearly state the issue you are trying to solve. Ask why. Start by asking why did this problem occur. Keep asking why. For each answer, ask why. Again, building on the previous answer. Reach the root cause. Continue asking why until you reach a point where the answer reveals the fundamental reason for the problem. So until you get the fundamental problem, it need not be 5 whys. It may be a more than 5 whys. Okay. Until you get the fundamental reason for the problem, just keep on asking the thing that will help you to have a root cause analysis. Okay. So the quality for a good quality Okay, so that's the main purpose they are giving here. Distinguish the causes from symptoms. Ensure you are identifying the underlying causes and not just symptoms of the problem. Work based backwards. Okay, review your answers to ensure you are correctly attributed each why to the previous one according to Julie. Okay, the 5 why technique is a simple yet powerful tool for root cause analysis, helping teams in quality control to pinpoint and address the core reason for the problems effectively. So the 5 why technique is a very best root cause analysis tool which can help you to identify the base problem. Okay, why this is happened fundamentally until the problem arises from where the problem fundamentally this has been arrayed out. Okay, so from where the fundamental base can be identified. That's the meaning. So coming to the real world examples, there are 4 industries they have stated here: pharmaceuticals, paint manufacturing, food industry, fertilizer production. And coming to the QC parameter, drug concentration. Okay, for pharmaceutical, this can be measured by UV spectroscopy, ensure dosage accuracy, paint manufacturing, viscosity or rheometer, control consistency. Food industry, the QC parameter, the quality control parameter is pH, okay, SPC, and ensure the shelf life and taste. Statistical SPC is a statistical process control. Fertilizer production, nitrogen content, the tool used is titration, meet nutrient specifications. Okay, quality control is a fundamental for reliable, safe, and compliant chemical production. It relies on well-defined standard, process monitoring, and statistical tools. Underlying quality control attributes. Okay, so the attributes and regulatory expectation help build the robust quality controls. Okay. Coming to the examples, they have given a one condition where the yield has been reduced between 78%, 94%, and 76% from 90%. Okay, in the last class which I told you. So the task may be apply the mass balance principles to identify the possible sources of yield loss and then suggest a quality control strategy using control chart to monitor the key parameters and detect the anomalies, and also based on the domain knowledge how the least charge principle guide process adjustment to restore the yield. So coming to the control of second question of control of pH in continuous neutralization process, when the sulfuric acid reacts with sodium hydroxide will give you a sodium sulfate is a neutralization process. During this process actually the pH is supposed to be between 6.5 to 7.5. If there is any variation, why this variation occurs, that need to be find out. What is the task, how to carry out this one? Derive the stoichiometric relation to calculate the required sodium hydroxide flow rate. Design a feedback control strategy to maintain effluent pH within the acceptable range. Propose a method for anomaly detection in the pH control system. Example, sensor drift or the valve failure. What is anomaly detection? Now, anomaly detection is the identification of unusual patterns or deviation from the normal behavior. So, underline the word deviation from the normal behavior of the process. So when this answer is here, that need to be carried out, find it out why this is happening. Okay, either by technique called Y techniques, 5 why techniques, or identify why this deviation occurs. Okay, so in chemical manufacturing, anomalies often signal equipment malfunction, sensor drift or failure. Okay, process instability, safety hazards, and product quality issues. In chemical manufacturing, anomalies often signal, so the deviation is because of maybe equipment failure or sensor failure or the process instability or safety hazard or product quality issues. So they detect the abnormal events early so corrective action can be taken, minimizing the downtime, waste or hazards. Coming to the types of anomalies, point anomalies, contextual anomalies and collective anomalies, which we have discussed very elaborately in the previous classes. Okay, coming to the rule-based approach, let's say you have want a temperature is greater than 75, 150 degree, I want an alarm when temperature is greater than 150. So use predefined threshold value. So I just put a 150 degree. Easy to implement and interpret, limited flexibility and prone to false alarms. Data different approach, use statistical or machine learning models to learn patterns from historical data. Better performance in complex and non-linear system. Example, data driven approach example is example train a model on normal process behavior and flag deviation automatically. So there is a anomaly detection by two methods which we have discussed in the previous classes. One is by statistical method, another one is machine learning methods. So either score method assumes the data is normally distributed, flags value the device by a certain number of standard deviation. Example, simple threshold detection in pressure or temperature sensors. Principal component analysis reduces data dimensionality, identify the correlation between process variables, Anomalies are detected when data points fall outside the expected variance space. Okay, use case is multivariate batch process monitoring. Coming to the time series analysis, models temporal behavior of variables with ARIMA or exponential smoothing. Detect anomalies like unexpected spikes, trends, or shift. Use case is monitoring reactor condition over time. Coming to the machine learning techniques, there are three techniques which have been highlighted here. One is isolation fuzzers, autoencoders, and short-term memory. So we have given an example for all these categories for anomaly detection, anomaly thing where it may happen in the distillation column because of flooding. So the principal component analysis with control chart can be used for the detection method. For batch reactor, temperature spike is a anomaly, is a deviation that can be detected by user score or LSCM. Mixing process, viscosity drift, autoencoder or ELG data will be help you to detection method to find the anomaly. pH neutralization, sensor drift, statistical process monitoring. Okay. So challenges in anomalies detection: false positive, false negative. Okay. Flagging normal data as anomalous, false negatives, missing real anomalies, concept drift, normal behavior changes over time, example due to catalyst aging, lack of label data. Okay, so supervised models require historical anomaly labels. Okay, that is very, very important. These are the things. Okay, so best practices and recommendation: combine rule-based methods with the data-driven techniques, use domain knowledge to select the relevant process variables, periodically update the models to account for process changes, integrate anomaly detection with the control system for automatic alert, visualize the anomaly scores for better interpretability. Okay, so the summary, the anomaly detection is essential for modern chemical manufacturing to ensure product quality, reduce risk of equipment failure, improves process safety and reliability. By using both statistical and machine learning methods, manufacturers can automate the detection of unusual behavior and take proactive measures. Case study 1, sensor fault detection in a heat exchanger system. A selective heat exchanger is used to preheat the feedstock before entering into a reactor. The temperature at the outlet is monitored by multiple sensors to ensure consistent heat transfer. So the problem is operators notice a gradual drop in outlet temperature reading from one sensor over several shifts despite no change in process condition or stream input. This caused the feedback control system to overcompensate, increasing the stream flow unnecessarily and rising the energy cost. So the investigation anomaly detection technique like statistical process control applied control charts on the temperature sensor data, principal component analysis, dimensionality reduction, compared the faulty sensor to others to identify the deviation from the correlated behavior. Findings: the fault sensor exhibited the sensor shift, a slow progressive error are not visible with the threshold based alarms. PCA flagged it as an outlier in the multivariate model, though the drift was within the sensor's raw specification range. Corrective action: okay, the sensors were recalibrated, redundant sensor and anomaly detection alert was added to the system. Okay, so redundancy, another sensor has been kept, okay, to take care of the things, and anomaly detection alert was added to the system. Chemical engineering principle use heat transfer despite the same utility input and design. Delta T discrepancy pointed to a measure issues, redundancy and reliability. Chemical engineers applied reliability concept to add backup sensing and improve the fault tolerance. Coming to the backbone, the case study 2, okay, in a batch polymerization reactor, producing polyethylene, parameters like monomer, feed rate, temperature, and agitation speed must be tightly controlled to ensure consistent molecular weight and viscosity. The problem is several batches fail to meet viscosity specs. Underline the word several batches fail to meet the viscosity specs, even though all set points were within the acceptable range. So the deviation were unpredictable and costly. So anomaly detection technique by using autoencoders, deep learning technique, trained on historical normal batch data. The model monitored multiple time series variables like temperature, monomer feed rate, pressure, stirrer speed to detect the abnormal patterns. The findings is the model detected the anomalous behavior in early phase heating in the failed batches, slightly slower ramp rate. This caused incomplete reaction initiation and low polymer chain growth. So the root cause has been found. A malfunctioning steam valve actuator delayed heating during the early batch stages. So why this has happened? So the corrective action is to replace the steam valve actuator. So because of the malfunction of the steam valve, the delayed heating during the early batch process, because of that the polymerization rate efficiency is not good. So the steam valve actuator was replaced. Real-time anomaly alerts were added to the early batch phase. Chemical engineering principle based on the polymer reaction kinetics and process dynamics. So the rate of polymerization is temperature dependent, especially in initiation. The process dynamics slightly delays in achieving the reaction temperature affect end product quality significantly in batch system. So the heat exchanger and polymerization are the two case studies which we have seen. The problem is heat exchanger is sensor drift, or the polymerization is a batch inconsistency. So the detection method of anomaly has been by used by principal component analysis or statistical process control for first case. Second case is autoencoders. The basic principle of chemical engineering principle which has been used is the heat transfer and control. Okay, and the kinetics and process dynamics for the polymerization. Coming to the third part, okay, which we have discussed, okay, in the third part of the unit 5 is integration of data analytics with process control, monitoring and control. So this is refers to a use of advanced data analytics techniques to enhance the performance, reliability and the efficiency of industrial process system. So what is industry 4.0 is like industry 1.0, industry 2.0, 3.0. Okay, first of all, the main thing they try to produce is steam. Okay, the steam production. From the steam production, they try to automate the vehicle like train. Okay, steam engine. Okay, industry 2.0. Industry 3.0, industrialization. 3.5 is a globalization. So now the people having a robot and things like that. So is a automated. The human intervention is very less. Industry 4.0. Okay, industry 5.0, like for example in medicines. Okay, the nowadays we need not go to the doctors and then ask the doctors will check for the diabetics and then inject. Instead of that, we ourselves can inject. That is called industry 5.0. Okay, so it's automatically self-centered. Okay, so the shift towards the industry 4.0 and smart manufacturing in the industry 4.0 is booming up in a developing nation. In the people in the western countries, they are moving towards industry 5.0. So we have discussed very elaborately what is industry 4.0. Coming to the traditional process control and the process monitoring. So traditional process control is open loop, closed loop control, PID controller, SCADA, digital control, distributed control system, super AC control and data acquisition. These systems are traditional process control. Coming to the process monitoring, use of sensors and data acquisition, key performance indicators and process variables, alarm and event management. So these are all process monitoring. What is data analytics? Descriptive analytics, data analytics, diagnostic data analytics, predictive data analytics, and prescriptive data analytics. So if we have elaborated, I've seen all these four types of analytics in the last class. Okay, I don't want to get into the deeper again and again. So it's a revision of what has been covered so far in unit 5. Okay, the techniques is a statistical methods, machine learning, artificial intelligence. Okay, so for the data analytics, why integrate with the control system, predict equipment failure before it happens, detect anomalies and drift in real time, optimize the process efficiency and quality, enable predictive and adaptive control strategies. Coming to the integration of the framework, data collection, data pre-processing, model building, decision making and control. Sources, sensors, PLCs, historical data, MES, challenges or noise, missing data, data volume. The PLC is the programmable logic controller. Okay, so data pre-processing, cleaning, filtering, normalization, feature extraction and dimensionality reduction, model building, time series models. Okay, time series data which we have seen actually in unit 4 elaborately, time series models, classification, clustering, regression. Okay, the tools are principal component analysis, artificial neural network, support vector machine, random forest. Okay, these are all supervised learning, right? So decision making and control, integrating the insights into SCADA and DCS system, closed loop feedback using predictive models, human in loop considerations. And coming to the case study, chemical reactor optimization, fault detection in heat exchangers. Okay, so in chemical reactor optimization, using regression models for yield prediction, real-time adjustment of feed rate and temperature, fault detection in heat exchangers, principal component analysis based on anomaly detection, alert integrated with the maintenance scheduling. Okay, so the predictive maintenance in pharma manufacturing, machine learning models using vibration and temperature data, triggering the condition-based maintenance action. So the benefits of integration of process control with monitor process control and monitoring, integration of data analytics with process control and monitoring. The benefits are increased uptime and reliability, better product quality and consistency, reduced operational cost and energy usage, enhanced decision making capabilities. Coming to the challenges and considerations, data quality and the sensor reliability, integration with the legacy systems, cybersecurity and data privacy, skill gaps and organizational readiness, tools and platforms, industrial platforms, OSI soft, PI system, Honeywell PhD, GE Predicts, open source, Python, R programming, MATLAB, TensorFlow, Azure IoT, Internet of Things, AWS, Greengrass. Okay, so I am not familiar with this, for example, TensorFlow, Azure IoT. Just go and explore, try to do the things. So whatever what I have covered so far is only the theory behind it. What are the things, how we need to in terms of chemical engineering principle. So you need to take out the case studies and then try to do the programming language and how this can be predicted. Anomaly detection can be carried out by using a Python or R programming. Just I just give it as a assignment. Okay, please try to submit the assignment at the earliest. So we need to submit all the data before 27th a year. Recently, I got a mail from the CEO office. Okay, so please try to submit your all your assignments along with try to do the MCQs. Okay, which has not been done so far. Okay, so with this future direction, self-learning control systems, digital twins, edge analytics, and industrial Internet of Things integration, federated learning, and collaborative AI for multi-site optimization. So the conclusion, integration of data analytics with the process monitoring and control transforms data into actionable intelligence. It is a key enabler of smart manufacturing, driving innovation, efficiency, and sustainability. Future trends and emerging application of data analytics in chemical engineering. So in chemical engineering becomes increasingly the digitized. Data analytics is playing a transformative role in design, operation, and optimization. Explore the upcoming trends and new applications that will shape the future of the field. Spreadsheet based data logging, basic statistical process control, present machine learning models, real time process monitoring, predictive maintenance, future is autonomous system, intelligent decision making, cross domain integration. Coming to the future trends in data analytics, digital twins, edge and fog computing, autonomous process optimization, AI driven process simulation, advanced visualization and augmented reality, federated transfer learning. Okay, these are the future trends in data analytics. Digital twins definition real-time digital replica of physical process or equipment. Application is reactor performance optimization, dynamic simulation. Benefit is improved design and real-time control application. So this all we have explained very clearly in the previous classes. So I just quickly go through the things and what has been as a revision for unit 5. Okay, so just go and refer back the future trends in data analytics like digital twins with a realistic example for each cases. Okay, and try to submit as an assignment. So that will help you to understand better and better you just write a code for all these things to identify the how this can be used in the real world examples in chemical engineering perspective. Edge and fog computing definition, local data processing at the edge of the network, near sensors, application, real-time fault detection, and corrective action at plant floor. Benefit reduces latency, improve response time. Autonomous process optimization, the technology is reinforcement learning, self-optimizing control. Application is continuous fine-tuning of chemical plants for efficiency and sustainability. The benefit is minimal human intervention, adaptive to disturbances, AI-driven process simulation, Aspen Plus and Aspen Isis. One is a static simulation, another one is a dynamic simulation. Future tools, AI-enhanced simulators for faster and more reliable design. Application, real-time simulation, assisted control and troubleshooting. Coming to the future trends in data analytics, advanced visualization and augmented reality. So the augmented reality and virtual reality, I told you an example during the last class. Augmented reality actually it will cover the real scenario and embed a digital object which is unreal. But virtual reality is totally everything is unreal. There is a difference between the virtual reality and augmented reality. The Pokemon Go is one of the game famous from 10, 15 years back. Okay, that was popular during that time. Then later, what happened actually? That one is diminished. Okay, that boomed up the augmented reality. Now the people have been seeing you could wear the special glasses when you go for a supermarket, a shopping mall, and things like that. the children may be playing. This all happen because of the augmented reality. Okay, so the tools are AR headsets, immersive dashboard, application is virtual inspections, operator training, remote control shooting. The federated and transfer learning purpose share learning process plans without sharing data. Application is corporate wide models for yield prediction or fault detection. Benefit detects data privacy while leveraging the global knowledge. Now, coming to the emerging application, green chemistry and sustainability. Application use emission tracking, waste minimization, life cycle analysis. Application analytical use is emission tracking. Application is sustainable process development and environmental compliance. Coming to the bioprocess and pharmaceutical manufacturing, the techniques are multivariate data analysis, model-based control, application batch process monitoring, PAT, process analytical technology integration, continuous manufacturing. Coming to the emerging application, okay, energy system and carbon management, analytical rules, real-time optimization of energy usage, carbon dioxide capture efficiency prediction. Example, using machine learning to predict the membrane performance in carbon capture units, process safety and risk management, data types, alarm data, incident reports and sensor anomalies, use case predicting and preventing hazardous events through pattern recognition, supply chain optimization, analytics use, forecasting, logistic, raw material availability analysis, tools, time series forecasting, digital supply chain twins. Okay, challenges and consideration during this process, data integration, diverse sources lab, plant ERP, require harmonization, ethical use of AI, transparency, bias in machine learning models, cyber security, data protection in Internet of Things, industry Internet of Things, and cloud environment, interdisciplinary skill sets combining chemical engineer with computer science and statistics. Skills for the future chemical engineer, Python language, R programming that is supposed to be they are familiar, process modeling and simulation like Aspen Plus and Aspen ISIS, knowledge of control system and instrumentation, communication and interpretation of data-driven insights. So in conclusion, data analytics is redefining what is possible in chemical engineering, embrace the hybrid skills and new technologies to lead the next wave of innovation in sustainable and efficient process industries. So with this, I just conclude the fifth unit. So all the best for your exams. I stop it here. I don't want to prolong the things. So it's a very longer section, almost 30 minutes for recapping of fifth unit has been covered. Okay, so please try to understand the concept and with realistic chemical engineering examples. Okay, try to understand the concept and then try to write the programming code which has been left over here for the fifth unit, and for the previous cases also. Now I am not much concentrating on the programming code. The program can we can very well can take it from chat gpt, provided you should know the understand the logic, need to know the syntax error, syntax if you want to learn from the thing that you can learn. Okay, so Python or R programming, or I just recommend you to use the Python programming to write the code for all this. Okay, so I already shared the material to some of the what is called data analytics and machine learning algorithms, okay, along with you regarding A star and U star algorithm and things like that. Similarly, machine learning support vector machine, k-means clustering, this algorithm just try to learn, okay, yourself. That will be helpful actually to do all this data analytics and machine learning. With this, I just conclude today's section. I'm in the unit 5, that is the overall all the 5 units have been covered successfully for this event semester 24-25. All the best for your final exam. Thank you very much.